Okay, so we have already seen that peculiar situation that arises due to the base field having finite characteristic, namely irreducible polynomials over such fields having multiple roots, which never happens if the characteristic is 0. And because of this reason, from now on, not only in this section but in this entire chapter, every field is going to be considered to have characteristic 0 unless otherwise stated, of course. Okay, so now our investigation turns into another notion. We already have, we have been seeing extensions of fields throughout this chapter. In fact, that's why it's called field extensions. Now we want to investigate some very simple extensions. In fact, the next notion is called simple extensions. So let's see what the thing is. These are extensions of fields which are as simple as you can think of. In this definition, however, the fields we are going to consider are not necessarily having characteristics 0, but it's generally for any field. But the results that we will consider, they will have characteristic 0 fields. Let F be a field an extension K of F is called a simple extension if K is equal to Fa for some A in K. So if you get the extension by attaching a single element to the base field, then such an extension is called a simple extension. Now here is this next very nice and important result involving simple extensions. This is theorem 551. Let F be a field of characteristics 0. And let A and B be algebraic over F. Then the extension obtained by attaching A and B to F is a simple extension, which is also because of that obtained by attaching, which can be obtained by attaching an element C to F for some element C in this extension. And whenever you look at the hypothesis says that F is a field of characteristic 0, but it also says that there are two elements A and B which are algebraic over F. But two elements where? Two elements in some extension of F. Because you see, if you go back to the definition of algebraic elements, you will see that two fields are involved. One of them is the base field F, and there is an extension K, and some element in K is called algebraic over F if so and so conditions are true. So that k is not being mentioned here explicitly. Okay, that's just it. So now we are going to prove this. And the proof of course goes like this. It starts from the fact that A and B are algebraic over F. Since of course I have decided not to write everything, but for this one at least let me write some things, because because you know that algebra, unlike analysis, is, I don't know, at least to me, is somewhat, what can I say, it is a little difficult for me. Okay, so let me just write it. It's more difficult than analysis. Since A and B are algebraic over F, there exist irreducible polynomials. Over F such that A satisfies F and B satisfies G. Why? Where are these polynomials coming from? See, because A is, say, let us concentrate on A. Because A is algebraic over F, by definition A has to satisfy a non-trivial polynomial. So if there is one such polynomial, then there will also be one such polynomial with minimum possible degree, and that minimality of degree would make that polynomial irreducible. So this is one such polynomial, irreducible, that is satisfied by A, and there is a similar one for B. So because these polynomials are non-trivial, so they will have degrees. Non-trivial means non-zero. Let the degree of F be M and the degree of G be N. Now, over some extension of F, has the extension been, it has been given a name, over some extension K of F, both Fx and Gx split completely. Why? We know that if we are given a polynomial, then there is an extension of the base field over which the polynomial splits completely as a product of linear factors, and such an extension with the smallest possible degree over the base field is called the splitting field of the polynomial. But how are we going to get such an extension simultaneously for two of them? That is rather easy. You just take the product of these two polynomials, then the product will have its splitting field, and that splitting field you can consider in place of k, so that splitting field will have all the roots of fx times gx, which of course are the roots of fx and the roots of gx. There may be repetitions, but that does not matter. So that's why there is some extension k of f over which both of these polynomials split completely. So that means whatever roots f and g are going to have, now they all will lie in k. So let us consider them. You see that one of those roots, among all the roots of f, one of them is a. Similarly, all the roots of b have, of g have b among them. So let the roots of b a, let us call it a1 since we will number a2 am, because there will be m roots in k, and the roots of g of x b b n, and these also will belong to k. Actually, I cleaned the board today, so I am being a little careful to wipe it so that it stays as clean as possible. In k. Now we invoke the hypothesis that f and g are irreducible polynomials. So we have seen that any irreducible polynomial over a field of characteristics 0 has only distinct roots. There is no multiple root, and that is that previous corollary that we saw. In fact, we can refer to that, since fx and gx are irreducible and f is of characteristic 0, corollary 1 to which result? It was lemma 552. Implies that these AIs are all distinct and so are the BJs. You see, some AI may be equal to some BJ. That may happen, but the AIs are distinct and the BJs are distinct. Okay, or in other words, this list has m elements and this list has n elements. Now we are going to look at a linear equation. Now, for any I in this range, and in the suffixes I am talking about, and j, where in case of j we will not consider 1. The equation We will see why suddenly we are talking about equations. The purpose will become clear. And the equation we are going to consider is this: ai plus lambda pj equal to a plus lambda b, where of course the unknown is lambda, and the equation is considered to be in K because the elements are in K. You understand that here the variable is lambda, or rather I should say the unknown is lambda, and this ai, bj, a, b, these are all of course are coming from K. That's why it's an equation in K, has only the solution. If you just simply solve it, because you are in a field, you can just solve it as if these are real numbers. ai minus a over b minus bj as the only solution, and this of course is again in K. You realize that we have taken j from 2. J is not equal to 1 means bj is not equal to b1, and that too distinctness of the bj's allows this to happen. Okay, so that's why we are able to divide by b minus bj, because it's a non-zero field element, and dividing by this actually simply means multiplying ai minus a by the multiplicative inverse of b minus bj. That's what it means. Okay, but what does this have to do with all these things? Now you consider the fact, now we are going to use the condition that f has characteristic 0. I mean, we have already used it once here, but now again, since f has characteristic 0, it is infinite. As a set, the field must be infinite, because finite fields always have finite characteristic. There are infinite fields also which may have finite characteristic, but finite fields always have finite characteristic. So if the characteristic is 0, and that too, if the characteristic is 0, then the field has to be infinite. So this infiniteness of the field allows us to choose one field element gamma, which will make this an inequality. What I am trying to say is that you can choose a gamma in K, which if you put here in place of lambda, you will not get equality, regardless of what I and j are. That is okay. Why is that happening? That's because you see, you are doing what? You are choosing pairs of suffix subscript values I and j in these ranges. So considering all possible i's and all possible j's, you will get such equations, many equations. Each one of them has one root. Now if you avoid all those roots, I mean all the roots are in K, but if you avoid all the roots and choose your lambda in F, after all F is inside K, right? And since F is infinite, avoiding all the finite roots, no matter how many there are, is possible. So if you do that and put gamma here, then because your gamma is not equal to any such lambda, you will always get inequality. And so we write, so we can choose gamma in F. If you are still a little bit uncomfortable about our choice of gamma from F, just consider that F is inside K, so ultimately we are choosing gamma from K itself. So we can choose such that AI plus gamma Bj is not equal to A plus gamma B for all I and all j in this range. Okay, now we are going to call this element C, and it is that C, we will show this, that if you attach this C to F, then that becomes equal to the extension F A comma B. Let C be equal to A plus gamma B. Note that gamma is coming from F, so ultimately gamma is again in K, and A and B of course are in K. Why are A and B in K? That's because K contains all the roots of Fx and all the roots of Gx, and this is the root of Fx and this is the root of Gx. So ultimately these three elements are coming from K, so this is in K, so that means our C is in K. Alright. So, and because of that fact, we are now immediately going to say something. Since A and B, well, we won't say that thing about K, but we are going to say this. Since A and B belong to this extension by definition, and gamma belongs to F, we have C equal to A plus gamma B again in this field. Do you see that infiniteness of F makes the extension K also infinite? So if we wanted, we could have chosen this gamma from K, but that would not have served our purpose because we want this. So now we have this. And so this extension of F is contained in this. Okay, because C is in this and F of course is contained as a subset in this, so the extension FC, due to its minimal nature by definition, is contained in this. Now we want to prove that the reverse inclusion is also true, and that will give us our result. And for that, now we are going to look at the fact that B satisfies the polynomial Gx, but slightly differently. Now note that B satisfies Gx. This is something we already know. Now what is Gx? Originally Gx is a polynomial over F, over the base field F, but it can of course also be considered as a polynomial over this slightly different field K prime where K prime is FC. It can be understood easily, right? Because since Gx originally belonged to the polynomial ring Fx, so that means the coefficients of G are coming from F. So in particular, the coefficients also belong to this slightly larger field. Thus, so B satisfying Gx over this field means what? It means that x minus B divides Gx in this. And now using the polynomial f, we are going to consider another polynomial h. Also, the polynomial hx, which is f of c minus, what was it, c minus gamma x. Okay, this is also a polynomial over this K prime, is satisfied by A. Let's see how. You substitute A for x, what do you get? Well, oh sorry, no, not satisfied by A but satisfied by B itself. So you substitute B for x and you get C minus gamma B. But C minus gamma B, by the definition of C, is equal to A, and F is satisfied by A, so this is 0. So B also satisfies this new polynomial again over K prime. So x minus B divides hx in K prime x. So that means x minus B is a common factor of hx and gx over this field K prime, or in this ring K prime x. Now, is there any other common factor that these two polynomials have in this ring? We are claiming that they cannot have. Let's see the reason. Now, for any j greater than 1 and less than or equal to n, of course, that is understood because we are going to now consider bj, the corresponding element bj. hbj, what happens to this? hbj, by definition of h, is c minus gamma bj. And what is this? This is not equal to 0, since c minus gamma bj is not equal to ai for all I in the range of I. Why is that so? That is because you see, what is C? C is A plus gamma B by definition, right? So had you, if you had equality here, you would then have A plus gamma B equal to AI plus gamma Bj. But that goes against gamma because gamma does not satisfy any such equation. So that's why we have this, and so we are having not equal to 0 here. But what is the implication of this? You see, no Bj is satisfying H. I should not say no Bj, but apart from B1 or B, no other Bj satisfies H. However, the only roots that G has are the Bj's, and the factors of Gx as a result come only, they arise from those roots. So that's why besides B, or besides the factor x minus b, there is no other x minus something, and as a result products of them that can divide the polynomial hx in this ring. Because otherwise, you see, besides x minus b, had there been some other common factor of hx and gx, some other common root of gx and hx would have been there. However, that we see is not possible. The only common root that is there is b. So correspondingly, the only common factor of gx and hx is x minus b. Hence, x minus b is the, okay, so if it is the only common factor, then this is the greatest common divisor of gx and hx over should I write like this? Should I use this language over some extension of, yeah, okay, over some extension of k prime. Okay, but why over some extension of k prime? Why not k prime itself? That question also comes, no? I am noticing that just now. So what we are saying, okay, so we have got two things, right? We are getting this. This divides gx, and this also divides hx, and these divisions are happening over k prime, or in other words in this ring, and then there is no other common factor. So does that not automatically make x minus b the GCD of gx and hx over k prime itself? What is the problem in that? Okay, let's go through the proof and then we will see what the problem is. So after this, Oh, there is one more thing that I forgot to write here. Fine, so we see that gx and hx have x minus b as a common factor, but there may be higher powers of x minus b that may also divide both of them, right? However, that is not possible. So let me just write here in brackets. Actually, it is written as a separate line before making this conclusion. Note that no higher power of x minus b can divide gx, for example. In particular, the square of x minus b does not divide gx, since gx has no multiple root, or in other words, all the roots of gx are distinct. And then you can conclude that this is the GCD of gx and hx. Over why not k prime itself, that I am finding a little difficult to understand, but let's just assume that over some extension of k prime. But then gx and hx have a non-trivial factor. This line we have to understand it properly. It has some things behind it. These have a non-trivial common factor which divides x minus b. So what is happening here? Let's write this condition first. The GCD of gx and hx is x minus b in some polynomial ring k double prime, where k double prime is an extension of k prime. In fact, it's that extension that we are talking about here, in some extension of k prime. And what we are now saying is that this implies that there exists a non-trivial, something non-trivial, say mu x in k prime x, let me continue from here, such that mu x divides both gx and hx. In k prime x. How is this coming? Where is this implication coming from? This is coming from a situation that we have already considered before, but let me again repeat it briefly. So we are now having this situation, right? To understand this implication, let us consider its contrapositive, which is equivalent to the implication. Suppose that there is no non-trivial polynomial over k prime that divides both g and h, or in other words, let us assume that G and H are relatively prime as elements in K prime X, that is their GCD is 1, which is the negation of this statement. That is, let us consider this. In this, but then you know that because this is a Euclidean ring, you then know that we have an equation of like this for some Ax and Bx in K prime X. And this kind of equation goes both ways. If two elements are relatively prime, then there is such an equation, and if you have such an equation, that also implies that the elements are relatively prime. And now you consider this larger polynomial ring. You see, your original Gx and Hx are elements here, and so are Ax and Bx, but as a result they are also elements in this larger polynomial ring, and because of that this equation can also be interpreted as an equation involving elements from here. But then you can use that property that when you have such an equation, then the GCD is also 1. So from this it follows that the GCD of Gx and Hx is also equal to 1 in this larger polynomial ring. If they are relatively prime in the smaller ring, then they are also relatively prime in the larger ring. Now you revert this back to the original form. What is the negation of this? The negation of this is that the GCD is not 1. That is, there is some common factor that divides both G and H in this larger ring, which is what you have now. See, this is a common factor that divides both G and H in this larger ring, but that would imply the negation of this, that is, there will then be a common factor of G and H in the smaller ring also. So that's where we are getting this mu x from. So mu x now divides Gx and Hx in this smaller ring, okay, but the GCD of Gx and Hx in the smaller ring, in the larger ring is x minus b. Now you consider this, there is one more step. This mu x is dividing Gx in this smaller ring means what? It means that g of x is equal to some polynomial times mu x in K prime x. That is, this some polynomial must come from K prime. But if it is coming from K prime, then it is also coming from the larger ring. So this division that is going on in the smaller ring can also be interpreted as going on in the larger ring. So mu x divides Gx in the larger ring. Mu x also divides Hx in the larger ring. But the GCD of G and H is x minus b in the larger ring. So by one of the properties of GCD, this mu x must divide x minus b in the larger ring. That's what we have written, that then Gx and Hx must have a non-trivial factor mu x which divides x minus b. Okay. But now you notice the fact that this mu x, the author hasn't given it any name, but just simply says a non-trivial factor. The mu, we are calling it mu x. The mu x is non-trivial, and at the same time it divides x minus b. because x minus b is irreducible, so that non-trivial factor must itself be equal to x minus b. Since x minus b has degree 1, that non-trivial factor must itself be x minus b. But then what? Then we are just getting the fact that x minus b divides gx and hx, but now in k prime x, okay, the smaller polynomial ring. And that is why the GCD of gx and hx is equal to x minus b now in the smaller ring itself is exactly equal to x minus b. So the greatest common divisor of gx and hx is exactly equal to x minus b in k prime x. Let me make a final effort to understand that part. Why not this immediately? What is the problem? I think I am almost sure that I am missing something trivial, which you may be able to see, but I am not seeing it right now. Thus, x minus b is a GCD of g and h over some extension of k. Why some extension of k though? No, I don't get it. But anyway, what is there in the proof, that we now understand. But now what? What comes after this? Oh, so now you look at this thing. We are now saying that the greatest common, oh, okay, yeah, I get it. You see, our b, right, this element b is not necessarily in k prime. You remember what is k prime? K prime is f of c. In fact, we are trying to show that b is in f of c. So we cannot say that x minus b, just from that part we cannot, simply because x minus b is the only non-trivial divisor of gx and hx, does not automatically imply that it is the GCD of gx and hx in this ring, because it has to be an element in this ring, no? But we do not know whether b belongs to k prime. So how can x minus b belong to this polynomial ring? So that is why immediately we were not able to say that it is the GCD here itself, but it is the GCD maybe in a larger polynomial ring given by an extension of k prime. But then using that and some more argument, we were ultimately able to show that yes, it is exactly the GCD in this polynomial ring itself, and that in fact will now let us say that b belongs to k prime. This means x minus b belongs to this. In the text, k, in place of k prime you will see k, but because I have used k in the beginning itself, which the author hasn't used, so that's why I am calling it k prime. And so b has, if this is a polynomial in this ring, so b has to come from k prime. Okay. And now what about a? Since a is equal to c minus gamma b, and c of course belongs to this field, this extension. Gamma also has been chosen from F, and we have now proved that B belongs to this. So A also has to belong to this. But now A is in FC, B is in FC, so or hence this is a subfield of FC, and this is that reverse inclusion that we wanted. Thus we now have equality, and that's what we wanted to prove. Oh, so what I was thinking as a trivial matter, in fact, is what ultimately gives us the proof. How foolish of me. But anyway, we now have the proof. And one can easily use this result and induction to have this natural extension of this result. Say, F is a field of characteristic 0, and let alpha 1, alpha 2, some finite numbers, say alpha n, these are elements in some extension of F, and they are all algebraic over F. Then if you consider the field obtained by attaching all of them to F, that is this field, then that is also a simple extension for some single element C belonging to this field. We are not simply mentioning it in passing, but one of the exercises asks us to actually prove this. Okay, so we will see precisely what the steps are for some and the section ends with this corollary. Let K be, these are not the exact sentences you will find in the corollary, but the meaning is same. Let K be a finite extension of F where F is a field of characteristic 0, then K is a simple extension of F. This, however, we we do not immediately see how one can get this result, although nothing about its proof is given in the text. But let's see, the proof is not that big or difficult. We fail to immediately see how to prove this because we are now not given an extension of f which is obtained by attaching algebraic elements a or b or maybe finitely many alphas, but simply a finite extension k. Okay, but then what? Then how can we proceed? You see, because k is a finite extension, so let us call this degree n. Okay, we know that n is a positive integer, n is some positive integer, and this means that there exist that many elements in k such that they form a basis for k as a vector space over f. That means any element in k is a linear combination of these elements where the coefficients are coming from f. Now you consider this extension of f obtained by attaching these elements of k to f. Okay, you see one thing immediately, because these things are all in k and f of course is also a subset of k, a subfield of k. So by definition this is contained in k. By definition means by the fact that this is a field, by closure property of addition and multiplication, this belongs to, this is contained in k. But the reverse inclusion is also true. Why? Because if you take any element in k, then that element is expressible as a linear combination of these k's, where the alpha i's are coming from f. And you can clearly see that this linear combination is an element in this field, and that's why k belongs to this as well. Oh sorry, this is not alpha k, and that's why you have equality here. But then also we are unable to immediately apply our whatever we have got achieved so far. Why? Because who is guaranteeing that these are algebraic elements over f? What about that? But that is rather easy. You see, say you consider k1, okay, and you consider the extension of f obtained by attaching k1 to f. This is a subspace of k over f. So its dimension over f will be less than or equal to, and it is finite after all. So that means this is a finite extension of f. But then by a previous result, that implies k1 is algebraic over f. Similarly, the other ki's are also algebraic over f. So that's why now by what you have done so far, this is a simple extension, that is k is a simple extension. So we get this very nice result that no matter what the extension k is of f, if f is of characteristic 0 and this is a finite extension, then K is just this for some suitably chosen C. Okay, so that's where this section ends. And after this we of course have exercises which we will solve in the next field update. And our next upload is this coming Friday. What is the date today? Today is Tuesday, no? So coming Friday. So Friday what shall we do? Groups, fields. Yeah, let us do vector spaces. We will do calculus afterwards. Vector spaces means we have actually completed the section, but there are exercises. So we will solve the exercises in the community section. So that's just it for tonight. And see you on Friday with that thing. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.